Okay, guys, so last time we did, in the last couple of classes, we covered the Brayton cycle and we did an example for the air. I told you that was the basic cycle that models any aircraft engine, okay, any modern aircraft engine. And I told you, so we went a bit not too much detail, but we made to the main line of it, okay? So the other big cycle that is important is one called the Rankine cycle. So why is the Rankine cycle important? Because that one is the one that models any type of steam machine. So you might think that steam machine today might be obsolete, but what is a nuclear plant? It's just a big steam engine, no? That is produced to create electricity. So we're going to do the Rankine today, see if we can do the example, and then we'll see what we move after that, okay? We can choose. We can go to the air conditioning. If you want, we can go to the cycle of a car to see what is the difference between a turbocharged, or I mean, between turbo or supercharged and so on. But today, let's do the Rankine cycle. So Rankine cycle. I mean, it's a multitude of cycles. You could spend just a whole class doing different cycles. We just need to pick, the ones we want to do, and that's it. Okay, so let's say, just like I mentioned, the Rankine cycle is the building model for any vapor power plant. So basically, steam engine, okay? Steam engine. Obviously, today we don't have steam engines, but let's say power plants, nuclear power plants, that's what they use, okay? All right, so what is the simplified model? So the simplified model will be, you have on top a boiler. Obviously, you need to boil the water. Wait, I'm going to start from this point. You can move. So you boil the water, so you have steam. This is going to go into, let's say, a turbine, which will be the one generating the power. Okay, so that's the one generating the power. Okay, in between here, what can you have? This can be moving pistons, and the piston will be moving the turbine, no? Something like that. Okay, so here we go this way. Then in this area, you're gonna need now to cool the water in a condenser. I don't want to cool it cooler because cooler looks like you go camping, no? With the eyes. So in this one, basically the function of this one is to remove whatever excess heat that is not used here. So Q out. Since I put the Q out, what is the function of the boiler? Is to put some heat in. And now over here, in between here, obviously you need a pump to take the water from the condenser to the boiler. And this one again is going to require power in. Now, generally, this power will be coming from where? From the turbine itself, no? Okay, but I'm not going to do a shaft over here. So we do here 1, 2, 3, and 4. So if I do now the TS diagram for this, obviously idealize. Let me try to do it big. Okay, so over here, let's do this first. So this could be a line P1 of pressure. And then you might have another one here. You remember the TS diagrams we have, or TVs, we have lines of constant pressure. Okay. So generally what happened is this. This is step one here. Obviously, this is the ideal case. So in the ideal case, what needs to happen? The condenser just need to cool enough the water to start being heated, no? In real life, it can go down, okay? So now the pump is gonna work without any loss, should be working isentropically, okay? So that means that we're gonna move here straight up to 2, and here we should have S1 equal to S2. Now we get to the boiler. So you see that you cool it there, but when you move it up to this pressure, the water is not going to be right about to boil. It needs to boil a little bit over here. And then it gets on the boiler. It's going to go from here to here. And as soon as it's steamed over here, it should be able to start running the turbine. So now it's running the turbine. The turbine, if it's an ideal turbine, this should be moving. So this should be working isentropically. So we have S3 equal to S4. So that means that S4 will be here, 0.4 will be here. And then we go back to the beginning of the system. Okay, so I don't want to add maybe too much to the figure, but what should be between 2 and 3? This is Q in. Okay, 4 and 1, this is Q out. And then whenever you have the two machines, remember we on the previous chapters we studied what is the isentropic efficiency of the pump, the isentropic efficiency of the turbine, no? Okay, so we should be able to use those relations over here. Okay, so let's try to explain a bit the process. Even though we just did, but let's just write it down. Okay, so let's say here processes. So we're gonna have 1, 2. What is happening? We go from P1 to P2, no? So this will be, and this process is isentropic. So basically this is an isentropic compression. If you think about it, the pump is almost acting as a compressor, no? Okay, but instead of air, it's water, so you need a pump. So isentropic compression. P1 to P2. Obviously, P2 higher than P1. Okay, in 2-3, what do? We add heat to the water, no? This is a constant pressure, all right? So constant pressure. Heat addition. So basically, yes, obviously Rankine units, and Rankine is because it's the same person. If you think about it, what was the main motivation? I'm trying to answer the question. What was the main motivation of developed thermodynamics? Remember from the beginning class, it said on the 18th century, what was the major problem they had? Water in mines, no? So the first engine they did were based on what? Steam machines. That's why you had steam locomotive. So these guys was one of the first guys working on the steam engine. So obviously, he's the guy that started with the steam, with the Rankine cycle. Okay, and there's some units of temperature given to him. All right. So constant pressure. Then what are you gonna have? 3 to 4 is what's gonna happen now into the turbine is gonna be an isentropic. Look at it, isentropic, if you want, instead of compression, expansion, no? Through the turbine. So instead of compression, let's say isentropic expansion. That then 4 to 1. You are cooling everything. So basically it would be constant pressure cooling or constant pressure heat removal or something like that. So constant pressure. How do we call the other one? Let's look at it, constant pressure. Heat addition, so let's say heat removal, okay? Okay, so hopefully by now we have done enough, but what should be the value of the, at the pump, the value of the power in? If we take the pump as the control volume, there is no heat addition, the power should be equal to what? M dot H2 minus H1, no? Okay, but basically, let's do the first one, but I'm not gonna do it for the other one. So let's say for pump, as control volume. So basically we take the pump here. One, two, pump as our control volume. And we write down the first principle of thermodynamics. What will you have? Q dot minus power dot plus M dot H1 should be equal to M dot H2, no? Okay, so we know the power, the pump requires power in. So again, is there any heat being added to this system? No. So basically at the end, we're gonna have that the power in is equal to M dot. So it's a minus sign. I move it to the side. So it should be what? H1 okay, so be careful here, but this will give you H1 minus H2, no? Okay, but let's be careful here. Okay, let's finish this and then we'll look at the sign. Okay, maybe I put at the end here. Okay, so similarly, for the turbine, boiler, and condenser, what are we gonna have? So we look at the figure, power out, should be equal to what? M dot so what we have? We have similarly, we have here H1 minus H2, we're gonna have H3 minus H4, no? So M dot, because would be negative, yeah. H3 minus H4. Okay, then the Q in the boiler should be equal to M. This time would be H3 minus H2. And the heat coming out the condenser over here should be H1 minus H4. Okay, so here's what I was keeping on my mind as I was writing all this stuff. We need to be careful with the sign convention. Because you remember the textbook sign convention is what? This is our system, the textbook using the convention that the work or the power out is positive, so the power in is negative, but on the other hand, the heat going in is positive and the heat coming out of the system is negative, no? So in this case, what is the turbine doing? What is the pump doing? The pump requires power, no? Yeah. So really, if you look here, if we do this calculation, H1 minus H2, this value should be what? Positive or negative? Should be negative, no? Okay. Does that make sense or not? If you have something hot, which one should be higher? The H one is very hot, one is the temperature is higher than T1, or one is lower. And that T should be higher at the higher temperature, no? So if you look at this one, should give you a negative value. But when we calculate the efficiencies, we're gonna have to take the absolute value. Yeah, okay. So if we look at the efficiency, So we say the efficiency, this is a power cycle, is whatever the net power generated, whatever we're using, divided by whatever we are putting in. So this is the power in, the one of the turbine. No, so the turbine, the power generated by the turbine, which is the out on the figure, minus whatever is used by the pump, divided by Q in. So over here, if you want to be safe, we just use the absolute values. So what will you have? The power out would be absolute value of M. What do we have for out? H3 minus H2 minus absolute value of M. Oops, in is H1 minus H2 divided by absolute value of Q in, which is H3. Wait, I did a mistake here, one of them. Out is H3 minus H4. Okay, so this is a 4 on top, and this is H3 minus H2. So over here, basically all the amps cancel out. And we end up with the efficiency to be the absolute value of H3 minus H4 minus absolute value H1 minus H2, absolute value H3 minus H2. I'm going to rewrite it on the next page, okay? Just to make sure that everything is clear. So all right, so basically we have the efficiency here is given by the absolute value H3 minus H4 minus H1 minus H2, H3 minus H2. Okay. Or what could we say? We could recognize that the Rankine, I mean, we should give you the same answer, but Rankine cycle is what? Is basically is used to generate power, no? So it's a power cycle. So now, what was the general figure that we used for a power cycle? Again, I'm redoing this because for the understanding, this is really important. A power cycle will always operate between what? If we have this, what is this? This will be the first principle of thermodynamics. But what is the second principle of thermodynamics saying? Is that every single engine always operates between two temperature reservoirs, no? One hot, one cold. That's why the efficiency cannot be 100%. So if you remember, if you look at the efficiency of this, what was the efficiency of this? The total amount of power you can get depends on the difference of the temperatures, no? This is the power divided by whatever we put in. And we say that this, you can write it as 1 minus Q out over Q in. So what is Q out? Q out, we just calculate to be H1 minus H1 minus H4, and we're just going to take the absolute value, okay? You can see the m's will cancel out. So I'm just going to remove the m's now. It will be minus absolute value of H1 minus H4 divided by the Q in, which is the absolute value of H3 minus H2, but that one should be positive anyway, but we're still going to take the absolute value, even though it's not needed. So H3 minus H2. Okay, so these two should actually give us a very similar result, no? Okay, if that is the case. All right, so let's do a problem. Always easier when we look at an example. And here I have an example which I made in purpose to take it from a different textbook. So we have to go to our tables, okay? Might be a bit more complicated. So in this case, they say consider a power plant operating on a simple ideal Rankine cycle. So example. Steam power plant, so it will be steam power plant that is operating on an ideal Rankine cycle, which is what we just did. Steam enters a turbine at 3 megapascals and 350 degrees Celsius. So basically, what would that be? For us, would be okay, so let's redo the figure again that we had before. That way we can put the values. So let's just redo. Let's see, what is that figure? Let's just redo this figure very quick. We can redo the top one and the bottom one. All right, let's redo both of them. Let's just redo these two figures, okay? Very quick. So let's say we have here a boiler. Then here we're gonna have the turbine. Here we're gonna have the condenser. And here we're gonna have the pump. All right, so we know that this is gonna generate the power out. This is gonna generate, this is gonna need power. This is the pump. The most important that I wanted this is to put the numbers here: 1, 2, 3, 4. So when I read the problem statement, they tell us that steam enters a turbine at 3 megapascals. So that means P3 is 3 megapascals, and that the temperature T3 is 350 degrees Celsius. So obviously, what is the state over here of the water? Should be steam or vapor, no? So supposedly, I'm guessing we're gonna have to go to the superheated tables, no? All right. Okay, what else do we know? And is condensed in the condenser at a pressure of 75 kilopascals. So once it comes here to P4, so there is a pressure drop. This is going to be 75 kilopascals. Determine the thermal efficiency of this cycle. So we need to determine what we just saw over here, the efficiency. But let's do the figure again for the example. I think it's always good. So in our case, what do we have? We are operating here at P3 equal to 3 megapascals. And our lower pressure here, let's say this will be what? P4 or P1 would be equal to 75 kilopascals. So as before, we go from here to here, then we go through this line. This should be 3 on the ideal case. This should be 4. We go back over here. Here we're gonna know S1 equal S2, and here S3 equal to S4. Okay, so now, as we saw over here in this page, we have 2 ways to find the thermal efficiency. So which way you want to do it? I mean, we could do it both ways. You can check it, but which one has less values to find enthalpies? This one or this one? Maybe let's do it both ways, okay? But you see, this one looks a little bit faster, no? So let's do this one first, and then we need to find what? So this one has H2, oh no, so we have the same values. We need to find the same values of enthalpies, no? So what we need to do is to find all the different enthalpies, and then we can use either one. All right, so let us find enthalpies over here. So let's say we go at state 1. How do we find H1? What do we know? What do we know at point 1? We know this is going to be a pressure of 75, and this should be saturated liquid, no? Okay, so we know state 1 will be, we know P1 equal to 75 kilopascal, and we know the state will be saturated liquid. So let's see if we go to the tables. Which one would that be? All right, so properties of water. I think we can go to the pressure scale. So table A3. Hopefully they will have the 75, and we don't have to interpolate. So table A2, table A3, we just pass it. So So how many bars will be 75 kilopascals? This is table A2, no? All right, guys, so we have 75 kilopascals, but we only have in bars. So one bar, as somebody mentioned, is 100 kilopascals, meaning that 75 kilopascals will be 0.75 bars. We don't have 0.75, but what can we do? What about somebody? We need to go here to the H fluid. So we like somebody to do 376.7 plus 391.66.
384.18.
Okay, and 391.66 divided by 2 give you, so up over here, interpolating from, but easy interpolation from table A3. So you get H1 equal to H fluid or H liquid equal to 384.11. Is that what you said?
384.18.
Okay, 384.18. Okay, so let's see. I'm going to find. Oh, we need to find S1, no? If we want to find this one over here. Okay, that one's going to be interesting. How do we find that one? So on S1, we also need S1. So you can do that. Would be as fluid. We might have to do it differently. I don't know if we're going to be able to find it with the entropies. We might have to use a specific volume, but let's try. So over here, I would like somebody to do S fluid will be 1.1919 plus 1.2329. 1.2124. Okay, so now at state 2, let's see if we can do it this way, because we know the pressures, but we don't know the temperatures. Okay, so let's see if we can do it not that way or not. We'll find out. Okay, so H2, what do we know? We know from the figure here, the problem is that we don't have tables of saturated water, and we don't really know the temperature. So we'll see what's gonna happen here. If we knew the temperature, it would be easier, but they give us the pressure. So let's see if we can do it that way. Otherwise, we're gonna have to go around another way. But what do we know? We know P2 is 3 megapascals. So conceptually, we should do it. And we know that S2 is equal to S1 is equal to 1.2124. Okay, so really conceptually from the figure, what should we do? We should go to this, let's say, the tables on this side, no? So let's see if they have them, but I don't think they have tables for that side, but we can try. So you see this one is pressure will be 3 megapascals. So 3 megapascals should be how many bars? Oh, here you have this stuff, we have the value here. So we have 3 megapascals. So how many bars would that be? So that means that 1 megapascal is, so 1 megapascal is 10 bars, no? So if 1 megapascal is 10 bars, and we have, how many we have here? So 0.3, 30, no? Should be 30. So the problem here, you see with the temperature, that gives the temperature, but I mean, we can do it approximated that way, but that's not going to be accurate at all. Because the 233.9 here should be the temperature where? Should be the temperature over here, no? Not the temperature over here. Okay, so there is no table, so it's table A3, table A2, and this is what? Temperature. Yeah, you see, this is the one in the middle, this is the mixture, but we don't have some of the other tables. Okay, so we need to find another way around, just because there's no tables, okay? All right. Okay, so the reason is because there is no table for this area here. Okay, so what we're gonna have to do is this. Because of the lack of tables for the liquid region. So basically, we have a table specific to this one and specific to this area, no? We have a table here. If we have the temperature, we can approximate it because this does not change much. But since we have the pressure, it doesn't help at all. So what we can do is as follows. So we knew that the work of the pump is equal to basically H2 minus H1 wait, I want to hear this efficiency. Sorry, I should have put the M over here, okay? Okay. Then what is in general the enthalpy? What is the definition? U plus P dV. Okay, so what's going to happen here? We can approximate this here. Wait, let me double check. Let's see if I have it somewhere over here. Let me double check. I'm pretty sure. Okay, pretty sure this is going to be basically equivalent to P2 minus P1, because we are working at the two different pressures. Okay, will be those two pressures over here. Okay, times the specific volume V1. Okay, because hold on 1 second. What is the way I did this is as follows. Okay, here this is the TS, but this could also be the TV, no? Yeah. So really here you could also have V1 equal V2 or V3 equal V4, no? So the total work, total power here, you can change, the pressure is different, but you can keep the volume constant. So I'm doing the change in pressure times the volume. Okay, that's basically what I'm doing. So that means, sorry for that, you're gonna have to give me another calculation here. That means here that V1 will be equal to V fluid. You have to give me that value. So that would be what? Table A3. We might go faster this way, table A3. So we were at 0.75, you need to do both of them. So V fluid will be careful here. So do 1.036. Okay, so it's 1.037. We don't need to do anything here. But now is it times 10 to the 3 or 10 to the minus 3? What does that mean? What is the trick that I told you to know that? What should take more space? Gas or liquid? Gas, no? Okay, so that means that this value here has already been multiplied by 10 to the 3, because you multiply now by this one, 10 to the 3, you're gonna have here 1022, no? And there is no way that the fluid will take more space than the gas. So basically we have 1.037, 10 to the minus 3. So from here, this means that the power in equal to P2 minus P1, P1. Scratch this one, please. I don't want to create confusion. So now we can do the numerical application here. So it should be equal to what? So we had P2 was equal to, in this case is, oops. Yeah, P2. So we have P2 from the figure, P2 equal to P3, no? So along this line over here. And P1 equal to P4. So P1 equal to P4. So this one is what? 3 megapascals. This one is 75 kilopascals. So that's going to give us, so the 3 megapascals, this is going to be, what was our table on in bars, no? So the 3 megapascals were what, 30? So we're going to have here 30. So 30 bars. But we need that to have that in kilopascals. Would be easier, no? Okay. Okay, so 3 megapascals, how many kilopascals would that be? If you know that, it would be 300, no? Okay. So then we have over here. I don't know, I was listening to you. So let's look at what is the unit transformation is. 1 bar. So is 1 bar is 10 to the 3 kilopascals. And what did I ask you is how many bars is 3 megapascal will be 3,000, no? Yeah, you're right. Thank you for was just listening. So this will be 3,000. So again, 3,000, I'm going from this line over here. 3 megapascal will be 3,000 kilopascals. And now 75 kilopascals. So we don't have to change that one. Minus 75. So this is kilopascals. Times V1 that we say is 1.037 10 to the minus 3. And this should be cubic meters per kilogram. So we do that, what do you get? Oops. 3.03, okay. 3.03 kilojoules per kilogram. Okay, guys, so let's do something here because since we have this new equation, let's go back to the notes that we had. This is power in. So we come back to this page over here where we had the isentropic. Okay, so power in on the pump, we could say was equal to what? This should be more or less equal to here, equal to, what did we use over here? P2, so it should be the amplitude, yeah, P2 over P1 times V1. Okay. So let's see, now I'll recall this one. So let's rewrite that equation. So P2 minus P1 times V1. This is going to give us 3.03. And this is equal to the m dot. We say, now the problem here is the order. Is this one?
Divided by m dot already because it's the specific value.
that one it would be divided by correct. See, absolutely right. So M, what I'm just trying to think now is that because of the sign convention positive, is this one the, I mean, let's go what we used initially. So the problem I have now is with the sign here for. So what would that be then? The pump is, do I need to use H2 minus H1 or H1 minus H2? That's the part here that. Let's try to put H, this one, and now basically we know the enthalpy needs to be higher. Okay, I have a problem with the sign, but I know what needs to happen. Here, which enthalpy should be higher, H1 or H2? 2, no? Okay, so we can find out if we're doing the correct sign or not over here. So basically now from this part of the equation, sorry for that, guys, I wasn't thinking about this part to be this way. From this part of the equation, we find that H, so we know H1, H2, okay, that makes sense now, should be equal to H1 plus the 3.03. Sorry for that. Okay, so at the end, we're going to have that H2 equal to 3.03 plus H1 that we found before to be equal to 384.18. So that gives you this, what, 387.21? Yeah. Okay, so, well, let's stop here for a second because we did a lot in here. Okay, so let's go back for a second. So over here, looks like before when I did the derivation of this one, we used this one, but I wasn't aware that we're gonna run into that issue in the prime. So we know that the power used by the pump, okay, is H1 minus H2, but because of the data they give us, we don't have the tables, we're gonna have to approximate this one as being equal to P2 minus P1 times P1. Okay, so now that's what we did in the problem here in order to find H2. Okay, so let's go a bit quick because we spent too much time on this one. Now for H3, what do we know about H3? H3 is going to be quick. What do we know about H3? H4 is going to be the pain. So what do we know about H3? We know the pressure, which is going to be P3. We finish it next time, but P3 will be what? 3 megapascals. And what else do we know? This would be saturated gas or vapor, no? Yeah, so let's say saturated gas. So here we could go to either table A3 probably. So table A3, I'm guessing again. And what we're gonna have, H3 should be equal to the H sub, instead of liquid, H sub gas at 3 megapascals. Yes, sorry for that. So we say would be 3 megapascals. That would be 30 bars. So it's over here. And the HG, let's see which column would that be, is this one over here. So I give us 2,804.2. And this should be kilojoules per kilogram. Oh, wait, no. Okay, we're gonna have to go. Let's do this one, then we go back. Okay, so I just saw something here. This is P. What is the temperature it's giving you here? 230, 233, no? Okay, so, all right, so sorry for that, guys. So really what's happening over here? Okay, I think next time I might just restart this program, but let's see if you see what is wrong in this figure. Because I think what confused me that they say ideal. What is this temperature over here? This is the one they just give us, no? Which is the 233.9. So this is a good example that you need to read the pay attention. So, but what is the temperature that we have? 350. So really we are a little bit higher over here, no? Yeah. So really the problem here when I read the stuff to model it as an ideal cycle, I did not pay attention, but really in our case, what's happening? Really our point 3 is over here, no? I mean, really it should be all the way on top, but should be right here and not here, no? Yeah, where this temperature here would be the 350. So that means that we need to go to table A4 for H3. We don't have the choice. So table A4. And basically we need to look at T3 equals to 3 megapascals. T3 equals 350. And let's see what would that give us, and I will stop over there, and next time we'll restart this problem. So we go to table A4 at 3 megapascals. So that was 30. So page down, so we have 30. And what a pain in the, that's not good. So we need to interpolate here. Okay, so maybe we do it next time. What would be the H is, oops, that's not what I want to do. I think should be what? VUHS, no? So should be this one. We should interpolate between these two here. So we have to interpolate between these two, no? Okay. So what about we stop over here and we start this one next time, okay? I think it started to get a bit confusing.